Welcome back. We are still on homework 1 in thermodynamics 2 and SDSMT. Homework 1 is on Maxwell's relationships, and this is problem number 2B. The reason why we're not going to do problem 2A is because I left it at home, my book at home. Or rather, I left my book at school. I'm at home. But I do remember what part B was. So it is Milo Koretsky's Thermodynamics textbook, 2nd edition. Part B states, prove this, or verify this, or show this, or whatever. That Cp minus Cv is equal to alpha squared times T over rho capital. Okay? So, how do we do that? Now, this one's a little trickier, okay? And we have to kind of look at our calculus cheat sheet and our thermodynamic web, whatever, to see what would be like that. Okay, how can we use our calculus formulations to get to that point? Okay, I will say that this approach is unique to this problem. We typically won't take this approach for most Maxwell's problems. It's just kind of unique to this one. But what I'm looking for on my calculus cheat sheet is something that has addition or subtraction. It doesn't matter, but as long as there's subtraction or addition. And there's only 2 on my sheet that have that. The product rule and the total differential. Now, if I look at those, I could probably try the product rule, but let me tell you, it's going to be the total differential. Okay. And that's how I'm going to do this. Okay? So, but, well, what is the total differential? It says that df is equal to df dx constant y dx plus df dy at constant x dy. Okay. Or f is a function of x and y. Okay. Well, which one should I use? What should be f? What should be x? What should be y? I have no idea. What I want to look for is, well, I got a Cp in here, I got a Cv, I got alpha T. Okay, well, let's look at the addition aspect of it. Okay, I got Cp's and Cv's. What is common between Cp and Cv? And I go to my measurable quantities, and so what do you see that's common between Cp and Cv? In general, in all these videos, if it hasn't been obvious already, when I pause, you pause the video and you think about what it is. Okay, so Cp, Cv. I look at the cheat sheet, what do I see? Oh, they all have T in common, but T looks more like a dependent variable. an independent variable rather than a dependent variable. Why is that? It's on the bottom. On the bottom means it's independent. So that's either x or y. Okay, so we'll just say that t is x. Okay. What about y or f? Well, let's look at the dependent variables. Okay, I got a u, I got an s, I got an h, and I got another s. Well, I've got 4 things, and only 2 of them are repeating. Or rather, one's repeating in 2 different ones. And what letter is that? That's s. So let's call this one s. So s is a function of t. Okay, so I got the 2, so I got ds dt at constant v equals cv over t. And I got ds dt at constant p equals cp over t. So it looks like I should probably have either v or p. Well, if I think about the addition, well, that one has a minus, that one doesn't, so, well, let's pick p. But in all honesty, it actually doesn't matter. I could do this with v, and I'm not going to, and get the same exact answer. Okay. So let's do, the total differential is s, a function of t and p. So I've got ds equals ds dt at constant p, dt, plus ds dp, constant t, dp. Okay. Now at this point, I have access to my full, suite of Maxwell's relationships and all that good stuff. So So I go through, so I have two relationships. I go through my checklist of Maxwell's questions. So, step 0. What's step 0? Funky functions. Is there a funky function? Nope. Step 1 is higher tier conceptuals in the constants place. Well, I got a P and a T. Are those higher tier conceptuals? No, they're not. Okay. HTC in the D place. Do I have a higher tier conceptual in the D place? I have a DS. Is a DS a higher tier conceptual? No, it's not. My higher tier conceptuals are U-Hag. Internal energy, U. Enthalpy, H. Helmholtz free energy, A. And Gibbs free energy, G. So, unless you're a Hag, you ain't a HTC. Okay? So, moving on. Do I have an S in the constants place? Nope. Do I have a DS? Yes, I do. Okay, and there's two ways I can get rid of a DS. And it's always dependent upon which one will get rid of DS. Okay. Well, actually not. No, I'll back up on that. Not exactly. But there's two methods. So what are my two methods for getting rid of a DS? One, Maxwell's relationships. And that's what I'm trying to say. Is Maxwell's relationships, I only use them if I get rid of an S. Okay? If I get rid of the S, Maxwell's relationship is the way to go. So let's look at ds dt at constant P first. ds dt at constant P. Oh, wait. Well, I don't have a Maxwell's relationship, but I do have a property relationship, Cp over T. And that does get rid of S, and so I'm good to go. Okay. That is, but that's kind of part of the other method, which is chain rule. And chain rule, I'm trying to get to ds dt at constant P, but I'm already there, so, well, I'm already there. So, ds dp at constant T. Do I have a Maxwell's relationship? Yes, I do. Does it get rid of S? Well, minus dv dt at constant P. Well, no S's, so that does. Okay. Step 5. Measurables, properties, or equations of state. Did I mention anything about an equation of state? Nope. In terms of my answer, are those measurables or properties? Now, all properties are measurable, okay, but are they properties or are they just measurables? No, those are properties. I have densities, I have kappas, I have alphas. And so I'm eventually going to want to simplify this guy, but right now I'm going to leave it. Because it might simplify something out and all the other things. I'm just going to leave it for now because I am not really at step 5 yet. I'm still on step 3 because I have a ds. So I need to figure out how to get rid of that before I start messing with this thing, okay? So, dt equals ds. Alright. Well, I got my Cp, and I know dv dt at constant P, so dv dt at constant P. So that's either going to be isothermal compressibility or thermal expansion coefficient. Which one is it going to be? Is it isothermal? Is T constant? No, it's not. So it's not isothermal compressibility. That means it has to be a thermal expansion coefficient. Okay, so that's thermal expansion coefficient. That's the alpha. All right. But there's even, well, it says it's supposed to be squared, so I don't even have enough yet. All right. That's interesting. I got all these dt's and dp's and ds's. Oh, those are goofy calculus constructs, right? Wrong. They're changes in s, they're changes in t's, they're changes in p's. And because they're changes, I can treat them like changes, I can treat them like variables, which means I can use algebra. Okay, meaning I can divide out. I can divide it by ds or dt or dp and get rid of one. Okay, well, which one should I get rid of, though? Well, that's kind of tricky, but let's think about what am I missing? Well, I got a v here, essentially, that's the inverse v. I've got a dv dt up here, so I could divide by dv to get another dv, but that doesn't really help me because I want to get rid of one. So I either want to get rid of dt or I want to get rid of dp. Okay, so but dp dt and dt dp is essentially the same thing. You know, just inversed. Okay, so that doesn't really help me. So let's look at the ds. What would I want to do with the ds to get one of these? Well, is ds related to density? Nope. Is ds related to kappa? Nope. Is ds related to alpha? And we're talking about directly here. Nope. Is ds related to cv? Aha! It is. cv over t is equal to ds dt at constant v. So that means I should divide by dt. Keeping v constant. So dt at constant v, dt at constant v, dt at constant v. And dt divided by dt, we already know that that equals 1. Okay. And we already know that that equals cv over t because that's what that is. So I've got cv over t equals cp over t minus dv dt at constant p dp dt at constant v. Alright. Or, oh, one thing I noticed, I don't remember, I need to look at my notes. If it seems like, well, what is alpha? Alpha, remember, is thermal expansion coefficient. Some books use alpha, some books use beta, and because I forgot the book at home, I can't remember what Koretsky uses at this moment in time. Actually, I have my cheat sheet. This should be a beta squared. Sorry about that. That's a beta squared. It's fine, I'm not going to start the problem. It's not like we haven't gotten to that point anyways. Alright. Alright, so I look at that thing. Properties measure. Now, if it was measurables, I'd be done. Measurable, 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 and measurable. But I'm not measurables, I am properties. Okay, so I have to go to that next step. Okay. So I go to my measurable quantities, and I look for where is a dv dt at constant p or a dt dv at constant p. I found a dv dt at constant p. That's isothermal compressibility. It is beta v. And I have, what about dp dt at constant v? I have one of those. It is beta over kappa. Well, so if I do algebra, okay, and bring that over, and bring that one over, and multiply by t, I have Cp minus Cv equals t times, two betas, okay, t beta squared v over kappa. That's not what I have up there, but is this a property? No, volume is not a property. Density is. So I have to change all my v's to densities. And now